直绕着它前面，给它快一个都快3分钟。
Okay. Okay, so good afternoon, everybody. Okay, so welcome to the second class. So the first one was a lot on systems. We'll do a little bit more about systems before we get into basic statistics. I hope that the systems part wasn't too scary for you guys. The statistics part then will be, I think, probably fairly straightforward for a lot of you. So a lot of you might have seen significant portions of it. The rationale for going over some of the theorems and tools in it is to make sure that we really all have a consistent common toolkit in terms of what we're going to use, later on when we actually design algorithms. Now, before I actually start with the lecture, a few important things. So DAPO's office hours are Thursdays, probably 1 to 3. So there weren't many people who actually requested a specific office hour on Piazza, so DAPO just decided, okay, Thursday afternoon is probably going to be the most convenient time for him. Check Piazza for the exact times. Homework problems will go live on Wednesday night or on Thursday morning. Okay, so they might be live already tomorrow noon, but you will definitely have them Thursday morning when you wake up. The same thing goes for some suggestions for problems and data sets. So we are going to make available things like the Yahoo Web Scope datasets. However, for those you need to actually sign on personally for a specific dataset. And the reason for that is that those datasets are of some commercial value, and basically what you'll need to agree is that you're not going to use these datasets to build a startup and compete with Yahoo. Right. So there are no real strings attached. It's just there to make sure that you're not going to do anything stupid with that data. Now, for the homeworks, we're going to do something, let's just say, slightly interesting. Because the issue is that we have a bit of a resource constraint in terms of who is going to grade the assignments. Okay, so we're going to use an incentive-compatible randomized algorithm to make sure that the homeworks are graded in a fair manner. So here's how it's going to work. DAPO is going to grade a random subset of your homework, which will need to be turned in 2 weeks from now. The date will be on the assignment sheets, don't worry. Now, at the same time, after you've turned in the homework, DAPO will release a template solution of how you could actually solve the problem. Okay. You're going to take that template solution, and you're going to grade your own assignments. Okay. So now you're obviously wondering, how can we make sure that not everybody assigns himself full scores? And on top of that, maybe some might be, very shy and always underestimate their own performance. So how can we be fair nonetheless? So what's going to happen is you're going to go through the template solutions, and using that and using your own solutions, you decide how much points you give yourself for each of the problems. Okay. DAPO is going to go and take these self-corrected assignments, which are going to be due the week after, again on Tuesdays, and cross-reference it with his sub-sampled gold standard calibrated solution set. And then he's going to use the ratio between those two numbers to recalibrate the remaining point assignments. So, bottom line of that being, suppose I'm a lazy bum and I don't really do anything, but I assign myself, full points. DAPO goes and corrects and sees for a subset of the problems that I'm not really doing anything. Well, he's going to scale down my full points to maybe 0 if I didn't really get any points otherwise, or 1 or whatever. Likewise, if I'm overly timid and I only give myself 50% of all points, but I really get everything right anyway, well, DAPO is going to scale it up. So you don't really have to be well calibrated. And there may be a homework assignment about that particular mechanism at some point. So this is an experiment. I hope it works out. But the advantage of that would be twofold. First of all, DAPO doesn't have to do so much grading. Secondly, I make sure that you guys actually look at the suggested solutions for the problem sets. So twofold advantage. I hope nobody is too unhappy about this. Okay, second thing, projects. So you guys can actually talk to me about possible projects. I'm here every Tuesday from 1 to 3. So I'm upstairs in Evans Hall in room 418. If you want to talk to me during that time, do so. That might make a little bit more sense after you see some of the data sets. There were 2 interesting suggestions on Piazza about what to do. One with regard to the user preferences sounded like a clear winner if you actually manage to get your hands on the data and do something moderately interesting. But talk to me in case you're not sure. That's it. You must absolutely complete the team sign up by next Tuesday. If you do not, we will take all the remaining students who have signed on for that class and just randomly combine them into teams. Right? And you may or may not like who you're working with. Okay, so it's in your own interest to actually self-organize. Piazza is a pretty good tool, I suppose, for that, or whatever else you're going to use, but do self-organize, please. Okay, good. Are there any questions with regard to last week before we move on to the technical content? Okay, good, then we'll just do that. The other thing is, stuff will always go up on the class website, on my own homepage, and there'll be an update log. So if there's nothing in the update log, you can assume that nothing has changed. Okay. So the one thing that we didn't do last time is talk a lot about databases and storage and so on. And I know for some of us, databases may not seem to be the most exciting thing, and I think you could have easily counted me among that group 3 years ago. And I'm not going to inflict a lot of SQL and so on you. So, well, the SQL is a sort of industry standard tool that a query language that you would use in order to drive a standard database like MySQL or Oracle or DB2 or whatever other tool that you might be using. And it has a very rich query syntax, so it's a programming language after all, so you could actually go and write the entire data analysis tools in SQL. Costs a lot of money, which you can see each time you drive down 101 and you drive past Oracle, you see that they're making actually a lot of money with that. Now, the problem is it's actually really expensive if you want to scale it, because it's basically one monstrous database. It needs to be all very coherent, and in many cases this is overkill. So in many cases it's enough if you have a key value storage. So the protocol is ridiculously simple, at least for the basic parts. It basically means you have 2 operations. One is put, so you put a key value pair, and the other one is get, and you get the value for a given key. Now put can do 2 things. It may either say, well, hey, I already have a value there, and by the way, I've overwritten one, or it might say, well, by the way, I can't really overwrite it because it's write locked, or some interesting things depending on how fancy you set it up. In the simplest case, if you put the key value pair, it comes back and says whether it's succeeded or not. That's all you get. Get, on the other hand, will give you the value for a given key, and if there's no key, it will come back and say, well, sorry, I don't have that key. Now, this is a lot more primitive than what you have in a large relational database. However, it may be just good enough for whatever you need to do. So then on top of that, there are slightly more fancy objects like Bigtable or HBase. So they aren't quite full databases, but they are not in the distributed key value storage realm either. And so you can actually go and create, change, delete rows. The data tends to be time-stamped. So for instance, at Google, Bigtable is scalable, sitting on top of the Google file system. So I don't know what architecture the current Bigtable is sitting on, but at least the published version sat on the Google file system. Now, you might want to use that, for instance, if you're crawling a web page and re-crawling it over and over and over again, then each time you crawl the page again, you dump the page content into the same row, just with different timestamps. You add all sorts of additional metadata, and those objects are set up in such a way that they can actually scale quite nicely with timestamp data. And of course, you can do everything in between. You might also want to have replication between colos. So colos is basically one big server center, and ideally what you want is that if your server center goes up in flames, your service still keeps on running. And the only way to ensure that is if you have a full copy of the entire system sitting somewhere else. It might be slightly stale, and you might have some glitches for the user, but that's much better than, you know, your site going dark for a day. And so then there are, you know, variable consistency guarantees. For instance, you know, if I write into two different databases, can I ensure that stuff still works? Okay, so what kind of attributes might you actually want to have for a key value storage? And this is really basic stuff, and all you really need to understand for the purpose of this lecture is just, you know, the basic protocol. So you put and you get. And some of the attributes might be that you have persistence. So in other words, you've written a key value pair, the machine goes down, and if it comes back up, you have it again. Replication, so that you may want to get in order to, you know, make sure that even if a machine dies, then, you know, as in if it crashes, comes back up again, or if it just disappears entirely, you still have the data. You might want to have high availability. That means even while some of the machines are down, while you get network partitions, you can still write. Transactions, you basically get a confirmation back that, you know, the write actually succeeded. And in some cases, you may want to be fairly specific about where you put some data. So like rack locality. So on the next slide, this guy, Hans Wagner Hansen, did a, I would say, labor of love, where he went through, I guess, 2-3 dozen different of those key value storage systems, or more generally NoSQL, and looked at various attributes and basically categorized them in terms of what they do. Okay, this table is there such that in case you ever need one of those, you can go back to the table and find the one that you want. So don't try reading it, it's just there such that you'll have it when you need it. Okay, what I'm going to show you is about the simplest possible of those protocols, namely Memcache. So who has heard of Memcache before? That's not bad. Who's used it? Okay. Okay, maybe about 5 or 10% have ever heard it. Okay, so this is a very simple system to get exactly those, you know, put and get operations done in a scalable manner. And we're going to use the very techniques that we discussed last time, namely consistent hashing, in order to see how we can actually scale up such a system in a highly reliable and, you know, scalable manner. Okay. Actually, the high reliability is something that you're going to do for your homework. So here's the idea. We have a whole bunch of servers and clients. Each server runs its own version of Memcache, and it supports those operations put and get. And as a matter of fact, Memcache doesn't actually give you any guarantees in terms of whether it will keep the data or whether it won't. So now the question is, how do we ensure that as I get more requests and I get more traffic and maybe get more inserts, I actually can scale? Well, that's very easy. This is exactly what we saw last time. We use consistent hashing. So I take my machine pool, M, and to determine where a particular key should go to which machine, the client runs an argmin over all the machines in the machine pool and then picks the one where it should go. So all the clients need to know is just, by the way, this is the list of all the IP numbers from all the servers. The servers themselves don't need to know anything whatsoever. I can just add an extra server here, and it will automatically attract more inserts. Now this is really good for a caching application, where it doesn't really matter so much if I don't really have some keys. So where would you use that? Who has used Wikipedia this week? I think pretty much everybody, right? Now, Wikipedia, if you look at the database access there, is very asymmetric. You have, on the one hand, a lot of people who read from Wikipedia. I think almost everybody here in the room read a Wikipedia article this week. Who wrote a Wikipedia article this week? Or edited one? No, but one. Okay. So, now what you can clearly see is there's a high degree of asymmetry between reads and writes. And if you're using a database engine to regenerate the page content for each read request, you're going to hammer the poor database a lot. Instead, what you do is the first read request as it comes in, I go and render the page. I get some, HTML snippets out of it, and I stuff that into Memcache. The next time somebody looks at the same page, well, all I have to do is I just check whether for that particular keyword we already have something pre-rendered. If it's there pre-rendered, well, wonderful. I just pull it out of the cache and display that. Now, what happens if somebody edits it? Well, that's a write request, and at that point you just invalidate things from the cache. So Memcache is a little bit smarter than just having a put and a get. You can actually also evict things. Now, what happens if we stuff too much things into the servers because, well, we don't have enough money to actually have all those servers? Well, it'll just start throwing out the oldest key value pairs. But those are the ones that are probably, if you have an LRU, least recently accessed caching scheme, those are the ones that you're probably less likely anyway to use. And this way, you can make sure that even though you might have a very highly asymmetric read and write workload, effectively a database is only busy with the things that it really needs to do, namely generating the page in the first place, and then incorporating the changes whenever they occur. So that's a fairly effective mechanism. Now, well, the other application where you could, for instance, use this for, so this is dynamic content caching, so the New York Times might be running something very similar, so whenever they write an article and the page gets updated, you pull it from that cache. But you can also use that, for instance, as a disposable storage when you want to aggregate gradients. And I'll show you that on the whiteboard a little bit on how it works, because we're actually going to get back to that in the optimizations block. So here's what happens. Okay, so I hope that the font size will be large enough this time. So if we have let's take a simple gradient descent algorithm, and well, you might argue whether this is efficient or not, but let's just take a very simple one. By the way, I'm going to write up to the bounding box here because that's all that fits really on the camera nicely. So let's say I have some function f of x that I want to minimize. And f of x happens to be given by a sum, I going from 1 to m, of fi of x. So that can happen, for instance, if these fi's are, the misclassification errors that they might incur when, doing spam filtering or content recommendation or, computational advertising, any of those things, where at least I have, by and large, a additive decomposable loss function. So now I'm going to go and break that into blocks. So I'm going to break it into blocks, I going from 1, so j going from 1 to n blocks, and here I have basically sums over the i's being in block j of fi of x. So this is one machine. And I have many of them. Now each of those machines, have their data. And furthermore, we can assume that this parameter vector x is actually fairly high dimensional. So this may very well, have size of maybe a gigabyte or so. Might be larger than that. But it's substantially large, such that actually just sending it between computers will take a long time. And let's say we have 1,000 of those computers. Okay. So what I would like to do is, for whatever reason, I would like to update x goes into x minus some number eta times dx of f of x. And it turns out that if this is actually strongly convex and actually has bound on the Hessian, you can actually get nice quadratic conversions for this. So it's not too bad. So you get linear convergence rates in it. But it's basically not a bad algorithm in certain cases. Now, how can we actually achieve this? Well, each of those subblocks, let's call those things fj of x, right, is going to give me a gradient. So at some point I need to perform the operation sum over all j's dx fj of x. Right. That's what's going to sit in each of those machines. Now what I need to do is I need to make sure that each machine gets the sum over all of those parameters. Okay. Basically each machine has one of those gradient vectors. Okay. Now, the idea is as follows. I first need to sum them all up, and that's very easy. Because I'm going to go and give machine 1 the first block of each of those gradient vectors. The second machine gets the second block of all. And the nth machine gets the nth block of all. So now how can I do this without causing a lot of point-to-point communication? I need to worry about scheduling and so on. What I do is basically I'll have each of those machines write individual blocks, basically fji, into Memcache. Now if I have 1,000 machines and this is a gigabyte, each of those blocks is going to be a megabyte large. And then I have the gradient aggregators pull 1,000 of those blocks out and compute the sum. Then they can go and push it back into Memcache, and the other machines pull them out again. That's fairly straightforward. Now, what's the advantage of this over MapReduce? Because after all, you could do MapReduce too. The advantage is that I preserve the state. So this is a very, very simple way of getting some idea of how you can actually build distributed systems fairly easily, which will perform quite a bit better than, let's say, simple MapReduce, and that are very easy to construct, because you don't actually need to go and implement anything of Memcache, you just download and install it. Okay. Any questions about that so far? Yeah?
What do you mean you preserve the state?
Okay, good question. So what it means is that each of those machines here that have this block fj of x, they may have done all sorts of optimizations on the data set. They may have, for instance, loaded it in memory. They might have created some index structure. They might have done whatever other optimization you might want to do. They might have tokenized the strings. They might have done feature extraction, anything you can imagine. Now, some of those operations are actually quite expensive. And if you manage to do them once off and then use them over and over again, your code is going to be a lot faster than a code which basically tears all that data structure down, discards everything, and maybe starts up the same subblock of data on a different machine. And this is one of the big problems if you use, for instance, just plain MapReduce, and you're going to suffer from that. Now, if you have only 10 iterations, well, MapReduce is probably good enough. If you have a couple of hundred iterations, this is going to hurt you big time. Okay. So, moving on a little bit. By the way, thanks for the question. Any other questions? Okay. So this is probably one of the most famous distributed key value storage systems. It's also one of the first ones that was described. Dapo found a nice blog post from Vogel. He's the Chief Technology Officer at Amazon where the system is actually going to be available on the Amazon Cloud service. So if you want to use that in any product that you have in a startup, you can now use a highly available key value storage system right away, right out of the box. Okay. Now, here's what it does, or why it needs to be a little bit fancier than Memcache. So Memcache is something that's not very reliable. Now, that's fine if you're just using it as a cache, but suppose I want to purchase some items on Amazon or any other e-commerce site. And it so happens that, some machines go down. Then if the user loses things from his shopping basket, chances are pretty high that he's not going to put them back, so you lose actual business. So it costs you real money. Therefore, operations like adding things to the shopping basket or removing them, or in a social network that I friend you, you really want to make sure they are stored no matter what's going on out underneath in the hardware. And so what can actually happen because of this is, suppose I have a network partition and two server centers are disconnected because somebody maybe cut the cable, right? You need a mechanism for reconciling two possibly different versions of such a state. Okay. Who has used SVN or Git or Mercurial or any version control system before? Okay, good. So you know exactly the problem. Two people are editing a file, they make changes in two different places, and then the version control system is quite clever because it figures out that different people have edited different parts of the file and it incorporates all the changes and merges them together. And some of the smarter ones, such as Git or Mercurial, allow you to actually fork things and then remerge. And this is essentially the same operation what's going on here on a record basis. And so there's some very nice theory, which I'm not going to go into. For that, you really should take a systems class. So there's something called Lampert clocks. And I'll just give you a very simple example of that on the next slide, which allows you to find out what the version history of things is, even though you may have actually had various partitions and mergers. Okay. So on the right hand side, this is from the Dynamo paper where they describe how Amazon S3 and so on, their system is set up. So they have some client services and additional routing structure. And then basically they have underneath those distributed key value storage instances, which store things like shopping baskets, inventories, and so on. Now, suppose we get some network partition. So this is a record, and it gets updated, and at time step 2 by machine X. Machine X, well, basically storage X holds the master copy. Then the update here, and again the partition gets handled by storage node Y. And here another one, because I have a partition, well, unbeknownst, gets handled by storage node Z. Okay. So now I have two inconsistent versions. How can I tell that they're inconsistent? Because what I'm going to do is I'm going to record who changed it and when the last time was that they changed it. And the only condition that I'm imposing on the clock is that it's always going forward. They don't have to be in sync. So now, if I realize that, well, I have those two records of the same object in storage, I need to go and reconcile them. And this can be handled at an applications level, or you can have a simple rule like what you do in SVN or Mercurial. And so I go and compile this, and now it actually has its ancestors, both these and these guys, so I take the union. So any other key that I might find in the system that can be seen as an ancestor of this, I know is automatically consistent. So if I find something that looks like SX, 2, so it would have been written before, and SY, 1, I know it must be automatically consistent with this. So that's actually probably one of the more ingenious ideas in the Dynamo paper, that they actually implemented that at good scale. They do a whole bunch of other things, and they have funny names for stuff that is actually quite straightforward in machine learning. So they have this thing called anti-entropy using Merkle trees. Now that's essentially system speak for, doing statistical inference about which state you might have. Or via gossip-based mechanisms to find out whether machines are alive. So a lot of this really gives you good opportunities for doing machine learning. Pursuing that in this class would be beyond the scope of the class, but this might actually lead to interesting research questions down the track for you. So if you're into systems, I would look into this and compare it to what people do in machine learning and statistics. Okay. Another tool, and I'll just give you the very high-level description of that, is Google Bigtable, or HBase, which is essentially the open source version that provides something very similar. So it's exactly this row-based database. So it's not a full relational database, but what you have is for each row has a key. And in that case, they store web pages, so they store it in the reverse domain name index to make sure that related pages are close by. And you have various anchors. You have for those columns. You can have actually an arbitrary number of them. The only thing is that the number of families needs to be well controlled. And then you timestamp each of those terms. And then it has nice mechanisms for traversing, let's say, a particular time range or a particular column family. And yeah, the internals aren't actually quite so important for the rest of this class, but I just want to show you this stuff such that you have a little bit of an idea of how those pieces relate to each other and what is available if you actually want to build something. Okay, to conclude, well, there's at the moment a little bit of discussion going on between, classical databases and NoSQL at the other end. So if you look at, for instance, Michael Stonebreaker's blog, you will see him actually making a very strong, coherent argument for relational databases, and there are a couple of blogs which make very coherent arguments for the opposite. And I think the reality is somewhere in between. So what you might look at is the relational databases actually provide too much in terms of, the security, reliability of operations that happen on them. They're very complex. On the other hand, they don't actually necessarily scale quite as well. On the other hand, NoSQL, well, because it doesn't actually have much constraints, gives you actually a lot of knobs that you can adjust and, provide very specific services. It has very flexible things, but then it's not so general. And so what you can do is actually do something in between. So for instance, Yahoo's own storage system, it's called Sherpa, uses something like that. It basically uses as the basic storage engine on a per machine basis MySQL, and then puts a NoSQL wrapper on top of it. So this way you don't really have to optimize and write and mess that much with the actual storage engine, but you just have to worry about the piece that is actually different and new, namely how to aggregate things. So there's a pretty picture of what this can do. And this concludes the systems part. So I walked you in the past 1/3 of the lectures through, well, a fair amount of hardware, what kind of data you might encounter, how you can parallelize and distribute things, store, process, and then in the end databases. Now you might really wonder, why on earth are we doing this? Are we in the wrong class, right? After all, this is scalable machine learning. Well, fortunately or unfortunately, depending on how you see it, it does require to know which machines the algorithms run on. So for instance, a lot of those parallelization strategies we're going to encounter big time again when we do data streams. Likewise, when we then look at optimization algorithms, we'll need to know a lot about parallel processing structures. When we then look at graphical model inference algorithms, we will borrow heavily from the distributed key value storage problems. And all of this, of course, is applied to the data and the type of data that I showed you before. Depending on how we go, we might have a chance towards the end at looking at some very, very fast probabilistic clustering algorithms which heavily rely on the hardware features that things run on. So there's a very clear connection between the algorithms that you will build and the hardware that it runs on. And if you ignore that, your code just won't be so good. So I know it's a little bit early to have a short break, but we can probably have a 5 minutes break right now, and then we'll dive right into statistics. And by all means, do ask questions if you have any.